unmute. Oh, right, audio.
Besides election policy.
Mic check. Yeah. Yep, that's good. Ah. Okay.
Anything else to announce, please?
This is gonna be muted.
Reading day activities?
This, oh, it zoomed out.
Oh, well, the full board's available now.
That's interesting. Okay. Just the social, the integration be the map 40/20 presentations and the 40/25 presentation.
What will be on the board?
Reading day.
Okay, yeah. Okay, hi everyone. Welcome to our last talk of the semester with Professor Lee-Peng Lee on logic.
With Jonah Marcus.
Yes. And before we start, I had a couple announcements I wanted to make. The first is that we have moved into our math club yearly election season. And nomination forms opened yesterday and will be open for the next couple days. And moving into our election starting next week, or next Wednesday specifically. Besides that, well, so everyone feel free to do your nominations, ask people for nominations, and the only restriction is to have come to at least 3 math club meetings this semester, approximately. So if you've been here, you should be eligible, and we'll make sure to make that happen.
But the guarantee is fill out the attendance form.
Very true. QR codes around you, attendance, that'll help us at least have your name somewhere so we can remember to include you. Other than that, some other announcements, other events happening next week on reading day specifically, which is a big day for the math department.
Which is April 20th, Thursday.
Yes, next Thursday. We have presentations all morning, 9 to 1 for the research capstones and senior theses. Those will be happening in 509/511 Lake Hall during that time period. Basically every 20-ish minutes that entire time. Also that day, there will be 40/25 presentations, TBD on time and room, but they will also be having that day. Math Club is hosting an event that day, that evening, our semesterly social, which will be in 012 Hayden, and from 5:30 to 7:30-ish p.m. And lastly, Professor Evan Dummett is hosting integration B finals that day. Nick, do you remember the room on that one?
Yeah, starting at 2 p.m. in 020 Dodge. So everything's gonna be posted everywhere.
All
Like,
the time. Someone
nobody
that
remembers.
that should be everything. And I'd like to give Professor the floor.
Thank you. Yeah, thanks so much for having us. So Jonah and I will do this joint talk together. He will do the hard part and I will do the easy part as usual. So let me just say a few words, before we start, right? I mean, how this came about. I think a few years ago, in 2014 or 15, there was a math talk by Professor Robert Case. He is retired now, and he talked about some foundations of mathematics issues, and which got me interested, in this infinitesimal and infinity, and so recently we met up again. Yeah, I'm going to pass you a drawing that he gave me, that is made by his grandson. And so, what do you think this is? For people who, okay, let me maybe right? Okay, it will pass to you, but if you can see it, what is this painting of? Right? Yes. There is a real prince there, yes. What else?
Or Turing and Robinson.
Yes. What else? A mountain. That's right. So this is does this mountain look familiar? Exactly. Except for those places, right? And yeah, so these are the 4 mathematicians which have let's say we have to do with the foundation of mathematics. And we in this talk we are going to talk about one of them. The first part will be like this. So Jonah here, does anyone know Jonah? Okay. Yeah, mathematics, the second year, who is also interested in logic, right? So we will have an interview where he will explain to us, like a few things about logic. And then he will show us the Gödel's incompleteness theorem, the proof of it. And then we will see, after that, we will see what we do, okay, depending on how that goes, right? Okay. So tell us a little bit more actually about yourself.
So, I'm a second year math major. I've been interested in logic for a while. In terms of classes I've taken, introduction to logic and advanced logic, but they're both in the philosophy department, so they're less on the rigorous side and more on like the philosophical consequences of logic, like what are we doing when we're doing logic. A little bit of self-reading, but yeah, that's basically me.
And note that we don't have logic classes, right? In math department, so you have to go to like philosophy or the next best thing. Okay, now can you tell us a little bit your own impression about the relationship between mathematics and law?
Yeah, that's a very large question. I guess the point of logic is to make math clear. It also gives us a way to determine when things are true. Because if we can reduce things down to logical formula, we can just say, oh, things are true because we can either construct it so it's the case, or that we reach a contradiction and then we pick out the contradiction and say it's true. So I'd say the main benefit of logic is clearing up our thinking and formalizing and being able to assert truths.
Yeah, so I think some people may have the impression that mathematics equals to logic. That actually is not quite true because there is informal, like more informal part of mathematics, right? We are going to learn, we're going to talk about Gödel. I just want to share one thing I read about Gödel. So Gödel, does anyone know about Gödel? Yeah. And what nationality? Yes. Neighboring, yeah. Austrian, yes. And so, what did he first study when he went to college? Physics. And then, but his interest with precision. So physics was not precise enough for him, right? So he switched to math, right? And then it was still not precise enough for him. So he switched to, there you go. So he became a logician, right? Okay. Now, this formality, this very rigorous, formality. Can you tell us more about formal systems?
So yeah, so I'm like historically, we started with formal systems. We started with like Frege and Russell, and with like naive secondary, what everyone's probably used to using. I mean, it doesn't work. You can't really work. I was gonna say you can't do a lot with it from everything. You can prove contradictory results as well, because of what Russell figured out of Russell's paradox, which is you can say the set of all sets that I don't can sell. I don't have any chalk, so you can't write it.
I know.
Yeah.
You can, yeah. Yeah, that's right. Okay, so did you just mention like Russell's paradox, right?
Yeah.
So at first the naive set theory, very simple. I'm sorry, did I miss that? You say like just membership?
Yeah. The only rule is membership, that you can just say it's either part of the set or not. But the idea is, and is everyone here like familiar with like predication, with like how to predicate over things? Okay, so You can predicate over any, like you can just say like, oh, anything's part of the system, so you can do the problematic set is also my handwriting's terrible, so is X squared.
Which I say, if you want to be a professor, you have to practice. It's not that bad, actually.
Trying hard.
Yes.
So it's that where it's like, it's a set of where the elements of the set are all the sets that aren't an element of it. So if it is an element of the set, then it's not an element of the set. And if it's not an element of the set, then it is an element of the set. That's not good.
So you are saying this, right?
Yeah,
You better remove him. Okay.
yeah, that looks better. But yeah, I mean, what logic and formal systems always want to avoid is self-reference. But once you refer to yourself, you can get something like this. There's a billion different paradoxes. Who is basically that most famously like the Leibniz paradox, where you say I'm lying. Yeah, if I'm lying, I'm telling the truth. And if I'm telling the truth, then I'm lying. Self-reference is bad. So yeah, that's like the.
So logic has a
Yeah.
fix for this.
Yeah, yes, in the fix is a type restriction. So. You can't, so you basically divide logic into. Simpler systems that can predicate over the lower system. So, the start is zeroth order logic or truth functional logic, potential logic. And that can only talk about individual cases, so. It could be an argument that if I fail my test, I'm sad. I failed my test, therefore I'm sad. And you can, yeah, modus ponens. You can write it out in terms of abstractly, or it's the form of argument that gives the argument truth. And so yeah, it would be if P then Q, P then Q. But the problem is you can't do anything with this. It's you can't do math, and then that's the point we want to do math. So we introduce first order logic where we can predicate over the elements of zeroth order logic. And probably the most famous first order argument is all men are mortals, Socrates is a man, therefore Socrates is immortal. Yeah. And yeah.
Yeah, so this is like the property of being human, man. So if X is a man, X is model for all men, right? So all men are mortal. Our mortals can be written symbolically like this. And then you say S, a particular person
that's
is human. Yeah, okay. So we do have this H of S, right? So H of S will imply that he is.
well, yeah, that's the conclusion. So if you the conjunction of those, but yeah, so it would be the classic, like the syllogistic way of writing it would be. So then that's
the conclusion.
Yeah.
Even these two things, then you have.
you have that, and you can always, one of the things that probably mathematicians are used to of saying that's like part of a particular set. And in logic, it's hard to talk about because there's a lot of different models in the way that you talk about things. So with this, we just specify a domain that it ranges over. So you just say S is in the domain, and that's true.
So the difference, right, between this lower order logic and higher one. Do you see the difference? After what we are telling you, here is quiz time. Even this example, right? What do you say that we had in the first order logic that we didn't have in the zeroth order logic?
We can assume implication.
We have implication.
We can assume implication as something that as a condition now.
Yeah,
Because we have quantifier. We have a quantifier. So we can say for all.
Right.
Right? Instead of just a particular implication, we can say we can, this is the, what you call calculation.
Yeah, application that you
uh-huh.
can. You can, yeah, first order logic can say the elements of certain of zero order logic satisfy their properties. And first order logic is quite powerful. We can do ZFC, canonical set theory with choice. It's called like a many sorted first order theory. So
I just quick question. So sort of another way to say that is you're by fixing the X in the first order logic, you are then getting the zeroth order logic.
Yeah.
Is that
yeah,
another way to think about that?
in the actual proof system, you can what is it called? Universal,
Yeah.
drop universal, and you just write S in there, and then it would just be a first order or a zeroth order.
That is a good way. So I almost want to say like, we can have variable, right? Here, yeah.
So yeah, so ZFC is a first order theory. It's all the many sorted first order theories. We're not just quantifying, like not all things we're quantifying over are the same. We quantify over elements or sets.
So we like to throw around, acronyms like this, CF. Are people, have you seen this? Okay, so stand for what?
Zermelo Franklin and choice.
Very good. There is an axiom of choice. Yeah. So basically, after they fix the naive set theory, this is the standard, right? The standard set theory.
Because it may be worth quickly going over CFC. I suspect there might be some people here who are completely unfamiliar. I don't know if it sort of plays in here.
Yeah, it doesn't really. I mean,
Yeah, it doesn't.
we'll talk about it later. ZFC has the same problems a lot of weaker systems have. It's like, I mean, how many people here are familiar with like arithmetic? So not that many. But it's like you can just do like as long as the system can do arithmetic, you get covered. There.
Yeah, I think the one thing at least you want to take home is that this is a standard set theory that people use, mathematicians use all the time, right? Which is fixed up, okay, from this naive set theory. So that is the important thing.
And there's stronger logics, but we're not talking about it. But
And the reason is that we can already do a lot of mathematics in this first order logic, with first order logic, right?
So yeah, we can do a lot of math, but of course, the point of this talk is that we can't do all of math. And we get Godel's first completeness down. I won't be talking about the second one. I know, shame. So yeah. Also, handouts.
Yeah. So maybe, yeah. So we have come to the point where, where Jonah is going to explain to you the proof of this incompleteness theorem. So basically, if you have a system rich enough, okay, such as CFC, they can do like reasonable things, reasonable mathematics. Godel say that there will be statements you cannot prove. Okay, that is the incompleteness.
True statements that you can prove.
You cannot prove within the system itself. So you cannot prove everything you can express within that system.
That like the like couldn't keep.
Yeah,
That is a great example.
it's both, yeah. That's a really complicated one because it's like you can prove that both its truth and its negation are both consistent with the axioms, but then we make other systems where we can prove that it's true and other systems that we can prove that it's false. So that gets really, confusing very quickly. But also, I should also before this go over the definition of completeness and sound. I mean consistency. So
you see,
yeah,
this is where, the continuum hypothesis, right? Okay. Yeah, this talk is fairly informal, right? In the sense that first it's math club. It's not like math class. And it is the thing we are talking about is a bit of a diversion in some sense, diversion to doing mathematics, right? Like we are taking a break and we are standing out a little bit further from mathematics and look at mathematics, right? Look at what is happening. Yeah, so yeah, I think it's good that we can address. So for example, you mentioned the continuum hypothesis, right? What's your name? Zach. Would you like to explain to tell us what the continuum is? What is continuum hypothesis?
I'm not sure definition that would be like
You know what
I
it
believe
is?
that yes. I believe that
Take like C and take like R.
Something or is.
Yeah. Yeah.
Okay, so first of all, yes,
Like,
that will be great. You are understand?
so.
Okay, so Sam is going to explain what continuum hypothesis is. Okay, so let me write down. You know, I'm sorry, just say what, let me say one more thing and then you will say. Recently, I heard that some people feel bad because when they come to a math club talk, they don't know what's going on. I mean, of course, that is going to always happen, like throughout your life. Like everybody, even your most esteemed professor, they don't know what's going on. Sometimes, at least. It's a relative thing, okay? You can always put them in a place where they don't know what's going on. So that itself is not a problem. But let's say, I'm thinking, in my math club talk, I hope that people know what's going on, right? Okay, so since we mentioned this continuum hypothesis, and you presented it as an example that cannot be proved or disproved, right? Using the standard set theory. And the fact that it cannot be proved or disproved has been proved. You understand that? That's the point about it. So that is to say that that notion is correct about, incompleteness, right? There are things you cannot prove. Yeah. Okay, but now same. I'm sorry. I'm sorry, Jonah.
Yeah.
Let's say what this continuum hypothesis is.
Like me to get up and write something with it, I guess, or can I just move here? So, this is I think one of the main results to Garrett Cantor, which is someone who's working in logic, I think the late 1800s. Some period, yeah. So he was asking, I guess, what are the, how can we judge the sizes of infinite sets? For example, like we have the natural numbers, 0, 1, 2, 3, 4, etc. And then we have the real numbers, which seem to have, kind of like a larger cardinality to them. So he asked, can we create like a one-to-one correspondence between them, which would indicate that these sets are the same sizes. And he found a way to prove that it is absolutely impossible to pair those numbers up one-to-one. You can always construct a real number that will not be in the correspondence. So he showed that the size of the real numbers is greater than the size of the natural numbers or the integers. So that is kind of the foundation of his idea. So the next thing is to ask, okay, if we have the size of the natural numbers and the size of the real numbers, is there maybe another infinite set that lies between them? That's the question of the hypothesis. He said, probably not. I think that the reals are just the next step up. But proving that is not possible.
Very good. So, does everyone understand what the continual hypothesis is? Right? So you need to have some basic, of course. Let's say here, this C here is what? The set of integers. This is the set of, and this sign here means cardinality or the size, right? So how many integers are there?
A lot.
Simply,
Infinite, yeah. And this one also infinite, but this one is bigger, right? If you know Cantor, there are different levels of infinity, so to speak. And the question is there a level between these two, right? And that is yeah, and that is the continual hypothesis, is to say that there is no, okay, there is no infinity between these two different infinities. And that has been proved to not, that no one will, that it has been proved that it cannot be proved or disproved.
Yeah, one of the things that's also important is that's not a matter of completeness, but rather expressibility of the system, because what was shown is that that both its negation and this actual statement is consistent with the axioms. So we don't even know if this has a truth value. It's probably, or actually it doesn't have a truth value. We can add it, we can add either one as an axiom to the system and do math anyway. So this isn't exactly a problem of completeness.
Wait. Here the speaker is okay, right? Because still some people think that the continual hypothesis may not be well defined enough to have, may not be definite enough to actually have a truth value, right? Then of course we cannot talk about it. But there are people who feel that this is a statement with a definite truth value, but obviously the axioms in CFC are not enough, right? So but it is something that is expressible in CFC, you see. Then I would contend that it is a completeness problem. I mean, it's relevant to completeness. That means they are statements which can be written in this, in the standard set theory that cannot be proved within that system.
Yeah. Okay, so before I go into the proof of Godel's completeness then, does everyone here know what completeness and inconsistency is?
Yes, or I should say that, but we should still
Yes,
define
I'll
it. We should
give
still
it. So consistency means that if it's provable, then it's true. So we can't prove contradictory results. Completeness means any true statement is provable. So a good logical system is both consistent and complete. So we can, yeah.
I've heard the soundness thrown around sometimes. Is soundness like just a synonym of one of these two, or is it related?
Okay. I'm pretty sure soundness is consistency, but like you look it up and it's like a million different, because it's like consistency. Logic's very complicated. There's a lot of like niche cases that you can find, but the way that they talk about it is in terms of consistency. Yeah. Okay.
So in a consistent statement, right, Jonah, you're saying that every provable thing is true, right? That is consistent. And in a complete system, every true statement can be true.
What is true?
That's you should take a philosophy class. I'm not going to answer that. So in logic, we'd say true is either we can construct it, or so we can construct a model where it is true, or we reach contradiction. So it'd be something like if we say, and this is why you prove anything from contradiction, if we have like P and then not P, it doesn't matter what's in here because we instantly reach contradiction and close the path. So truth and logic is very formal, but it's still very complicated, and I'm certainly not qualified to answer it. Yeah. Yeah, okay, I'm not getting into it. So yeah, on the handouts that I put out, there's the battle plan. Explains just the basic like rest of the argument. So it starts by creating a one-to-one mapping between the formal system that we want to improve and is capable of arithmetic. And then we want to construct a formula that can talk about provability. And then using that provability statement, we can create a self-referential formula. But rather than it being directly self-referential, we can use our Godel method, which is a subtle way to kind of walk the line and not actually formally self-reference. Well, we can do it within the system and it proves it's complete. So yeah.
I'm going to just write down the theorem. So
Oh, yeah.
people know what we are doing here. Yeah, you can, yeah. So any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is incomplete. Okay, so to say simply, meaning any system that you can do significant mathematics, right? Like that is not too simple, will be incomplete. Of course, there will be complete systems, but those are too simple. Those are like useless for math. But any useful system, yeah, any system that you can do useful mathematics will be complete. Okay? So I'm saying it colloquially, in a very informal sense here. And Jonah will give you the proof.
Yeah. So first, I mean, what we want is a function. G, I don't want to write Godel a million times, so it's going to be G. That takes from our system, call it S in actual numbers. Then on the sheet, there's the table, and that's where we associate each sound in the language with a number. And then to create this mapping, I mean, it's explained on the sheet, but so and it gets, the numbers are very large. It's the point is that this can be done in principle. So there's the example of G of E of X would be equal to, and then we go through the first go to each position, we raise it to a higher power using the fact that we can factor things sometimes uniquely would be equal to. So 2, 8, 2 to the 8, 3 to the 4. Yeah, and 5 to the 13, and then 7 to the 9. So that's just for that, and that's already a big number. And looking at the other thing, the full argument of being like there's this e to the x, that x equals x, and it's on the statement, it gets even larger. But also, what we want to be able to do is talk about proofs, and one of Godel's insights is all a proof is a list of symbols or a list of statements, and then that proves the last symbol or the last statement in that sequence. And then you do a similar thing for this. So in this one, I say the comma's not a symbol. That's just part of the sequence. So if we raise the numbers to a really high power. And yeah, the idea is that it's 1-to-1. And what's really important about this is that it means that so what's important is there's a unique relationship in between statements. So when we can prove something, you know, there's a certain property of provability in that relationship between the two numbers. And since this mapping is 1-to-1, it preserves the uniqueness. So in principle, we're able to see provability through over the map. So if something's provable in here, we can find its Gödel number, and from that number, in principle, we can figure out that it's provable in there.
It has a certain relation.
Yeah.
Uh-huh.
So, and yeah, I mean, I find that super interesting because we can talk about things so abstractly in that way. But so the second step of this proof is that we need to make a statement and talk about provability. Ideally, and I pointed out in the page, we want something that just can say like P is related to X because it proves it, but we can't do that because that's the type restriction. Like we can't just directly talk about predicates like that. But we can move this problem into the natural numbers using the Gödel number. So instead, we do an argument, we define proved equal to there's where G is the map. So, and that's the provability thing. Provability, symbol of provability. So this said a Gödel number that is part of Y, or the Gödel number that corresponds to Y. Sorry, yeah. The Gödel number that corresponds to Y proves is in the provability relationship to the Gödel number that corresponds to X. What are X, Y? So yeah, X and Y would be so. In this case, I mean this kind of colloquially, these should be Gödel numbers. So they're going to be just really, really big natural numbers. It's also important to realize.
X and Y are statements, right?
No, they in this the way that I read it is that it's equivalent. I should say it's equivalent to that, not equal, because if there's statements we can't talk about it, because then we'd be predicating those statements.
Does this require that the proof sequence begin the statement is unique?
No, or yeah, no. Sorry, yeah. It doesn't need to be because we're just talking about simple. There's no semantics.
Right, so can it occur in any proof sequence of a statement?
Wait, sorry.
If proof of X, Y
Mhm.
it is related to this, does
Oh, are you asking? So yeah, is it that everything that has a proof has a Gödel number?
right, no, so if Y isn't in the proof of X per se,
Mhm.
is it in any proof of X? Or every proof of X? Or
I think that's actually a good question. I think you could. I guess it would be an argument set because there are multiple proofs for X, but I don't think. In principle, it just matters that something exists, right? Because it would be when you say like, oh, there exists an X that satisfies this condition, that just rule out the idea that there's more than one X. I think there was another follow up.
It's.
Yeah, sorry, yeah. Don't think too much about it. So. And what's really fascinating is that it's a very complicated relationship between these two, but in theory, it's the same as saying like, oh, for existing X or for all X, for existing Y, such that X plus Y is equal to 0. It's saying that there exists an X and there exists Y is the same thing as saying something like this. All the proof relation is asserting that there's some arithmetic relationship between X and Y.
And can you explain what the turnstile on the board is?
Wait, which one?
The turnstile, like the sideways T.
Oh yeah, that just means this proves that.
So those are statements or proofs. I mean, these.
Oh yeah. Yeah, these are statements.
These are statements.
Yeah, those are the proofs. pointed that out.
Is there some like well-formed condition on like model?
Yeah, there is, it's, because you can. Yeah, you can go remember anything, it's just not gonna have a proof, because I mean, you could do something like. Like you could just write out a bunch of symbols and it would have a girl number, but it's like, yeah. It's not a bidirectional map, it's just one-to-one. So, yeah, I mean. You know, so the final part of the argument should be coming up with a. I don't know, should be coming up, creating self-reference. So if we talk about, we can, so. Wait, so. So this would translate to the girl number, or this doesn't have a proof, is what it would be. And that's a non. So this is not, these are not in the proof relationship to each other. That's all that's saying. So what we want is to say, how can we create a relation that says this statement is unprovable? And it would be, I call it you, or I actually don't call it you, girl calls it you. He gets a that equal to all or small. So this says at where, and these are both girl numbers. Neither, so and this is saying there exists no n such that n is the girl number of the proof of x, or the what in the statement world in the language. Yeah.
What is x? Is it just something arbitrary? Is it false?
Oh, that's a predicate. So, and the reason why we can just write f is because in the formula it just takes you write it out symbolically and it just has a certain kernel value. It doesn't really matter what the n is being figured out.
This is a much stronger condition than saying that it's not provable, right?
This is no, this is just saying that it's not, or there's yeah, there's
It feels much stronger in the sense that it would say that this statement is not and cannot in any way be involved in the proof of.
No, or rather, there is no statement that can prove this.
yeah, it's
excluding the provability of the statement.
yeah,
When you say for all n, right?
yeah, because yeah, the way Godel thought about proofs is that it's just a bunch of statements that connect to another statement.
Right, so this tells us that it can't occur anywhere in that sequence, right?
Yeah, we're just saying that x cannot be proved. This is x cannot be proved. So
He's asking whether this is stronger than
Yes.
necessary. Well, at least it is strong enough. Yeah.
yeah, yeah, I don't think I 100% understand, but it's later. So, but now we consider the statement of yeah, so it's not provable if the girl number of you is not provable, which is saying it's basically the liar paradox. And yet again, it's predicate, so it doesn't take a value on it. And this essentially says, I mean, very informally, it's like I'm not provable. And I could go through the proof of showing that it's actually unprovable, but it's basically if it's provable, then it's unprovable. And if it's unprovable, then it's provable. But we know it's unprovable, so it's true. It is a true statement, and this is a creation. of a true statement that cannot be proved with the system. So the system is incomplete, and necessarily so.
That's great. Very good. Yeah. Now you can sit back and relax. Yeah, we just have a few closing things. And I just want to remark that I discussed this with Jonah, right? Like this kind of also a self-reference kind of thing. This is allowed. And it is allowed by going to Godel's numbering, so that you create something else that refer to yourself. Okay, so it's yeah, and that of course is the genius of Godel. Yeah, and so in the last few, yeah, okay, I'm going to give you another way, okay, to understand this, okay, and this is due to this guy. Have you heard of him? Ryan Raymond, yes. You even know his first name, yes.
There's a book on combinatorial logic that I'm reading that's inspired by some of Williams' books, and I think that's I don't know exactly how you pronounce his last name, but you know.
I don't know either. I'm not the only one. Yeah. That's right. So this guy is actually he died not too long ago because he lived to like almost 100 or something close. He was a logician and he has written many books. And one of which is, gives this very interesting explanation of the big idea of the incompleteness theorem. Okay, so let's see. And it doesn't have Godel numbers and all that thing, which Godel actually did. Okay, so it's really nice that Jonah, did this for us. So I say, he's doing the hard part and doing the easy part. So this is supposed to be an easier crack at the thing. Okay, so consider a machine. Okay, so we have a machine here. And this is a machine that just prints things. It can print and only exactly 5 symbols and nothing else. Okay, so these are the 5 symbols you can print. And you can print string of it. Now, and okay, so now the next thing is this. Of course, okay, then we have an expression. Okay, what is an expression? An expression is just it's just any string, okay, made up of this, right? But apart from expression, we also have another concept, which is sentence. Now, a sentence is much more restrictive. It can only be one of the 4 following forms, right? So now you see, I only use 3 of the 5 available symbols here, right? What do you think is the meaning of this sentence? X is printable. Okay, so this means X is printable. Yes.
Here does X just.
Yeah, absolutely.
Connecting a string.
Thanks for the observant student here. Yes, this X must be break up. This X is a string, okay? Just an expression. Absolutely. So this means the expression X is printable. Okay, that is a sentence. Now, what do you think this is? Oh, this N here, yeah, so I should say, next we have a definition. So norm of an expression, so X is an expression, is X of X. Okay, this is what we call a norm of X. All right. Okay, so the norm of X is X of X. Now, here, the second sentence, the second possible sentence is Pn of an expression. What do you think this means?
This question about norm. When you say X and X,
Yes.
how are we If X doesn't take an argument, what does that mean?
What do you mean?
Well, because X can be any string.
Yes.
So what does the parentheses imply here? Are you just concatenating them?
Because these are the things we can also use, right? The parentheses, yes.
So is that just a string?
So let's say, tell me what is the norm of so for example, actually these I'm going to use. Okay, so what is the norm of what is the norm of this? Okay, what is the norm of this?
Just be tilde P and open parentheses, tilde P and parentheses.
Very good. Exactly, just like this. Okay, is it now clear? Okay, very good. Thanks for asking. Yeah.
Except for follow-up question, so if you have the norm of P, is that a sentence?
So norm of P it is not a sentence
Okay,
necessarily.
but, okay, that's good,
Do you see?
yeah.
Yeah. Okay, right? Because this is not a sentence. Well, I haven't given you all possible sentences yet. So that's a bit premature. Yeah, but it may not be. Okay, but so we have a definition. It doesn't have to be a sentence. You can norm expression. Okay, that expression doesn't have to be a sentence. Only one. Okay, now what do you think this? If this means X is printable, this means
Not printable.
well, N also stand for
Oh, no, wait.
norm, right? The norm of X is printable, right? Now, because look, Zach, we have this thing. What do you think this represent usually? Not, right? 30, 65 students, not. Yeah, okay. Yeah, so we have X is printable, the norm of X is printable. And then, okay, now it should be all very clear. What does this mean?
I mean, X is not printable, but also you have the norm of X is X of X. And now you're saying that the norm of X is N of X. Which one is it?
Yes.
Both.
Okay.
That is a very good observation. In fact, I asked the same question. That's how I know it's a good observation. Yes. Right? Excellent question. Okay, now finally, it must be this one, right? Yes, the final possible sentence. And this means what?
Not printable.
Okay, now comes the magic, right? Which is like, okay, yeah. So first, so all printable sentences are true. Okay, so this is a machine that prints only true sentences. It's like a very honest person that only say truth.
So do we mean, as when you say that, that would mean a machine that checks if true and then only prints if that's the case. But we mean anything that it prints is by default true.
Yes.
Okay.
Precisely. If you see it printed, it will be true. Okay? Now, comes the thing. We are going to show you a sentence which is true but not printable. Do you see? We don't say that if you are true, you'll be printed. Just that if it prints you, you are true, right? So here is a sentence which is true but not printable. In fact, do you want to come? This problem was too hard for me, so I just look at the answer. I mean, Marian presented it as a puzzle. Oh, you are so good. Whoa. I feel so embarrassed now. No, no worries. Yeah, I'm used to it. Okay, so no, yeah, not PN. You mean this? Right? Okay, we need. Yeah, we will also finally figure it out. Okay, so first, right, what does this say?
It says that not PN is not printable.
The normal.
Yeah.
Yeah.
Okay, so translate to what the norm of not PN is not printable, right? Okay. So the norm of not PN is not printable. Now, when is this true?
It prints.
When it prints. Okay, so the thing is, this sentence here, okay, so let us do it carefully. Because I'm always tripped up by these things. So this sentence is true if and only if, first thing, by definition, right? This sentence is true even, it's just meaning here. So if and only if the norm of Pn is not printable. But the norm of Pn is precisely this. You see? This is the norm of not Pn. Because what is the norm of x? It's x of x, right? That is why your observation was very,
Should one of those not have the not sign?
oh, it's just like this.
Because it's true if and only if it's printable. Or not if, oh.
Okay, so this is, yeah, this is saying, in words, just this, right? The norm of this is not printable. So therefore, this sentence is true even and only if the norm of, even and only if, yeah, the norm of this is not printable, right? You see? Okay. Or we can, yeah, that's right. True and only if, my goodness, I'm just repeating myself here. Is yeah, this is saying, okay, now we interpret, there are two meanings to this, right? Phrase we have, yeah, and we have noticed. This also means the norm of this. You see? So therefore, this, if we think of this sentence as just the norm of this, then it is, then this thing is not printable. So this is true if and only if the same thing is not printable. Okay, now that means they are both true or they are both false. Do you agree? Now, there will be a so either the sentence is true or not printable, right? So this very sentence here, right? So we have two possibilities. Either it is true and not printable, right? Or it is false and printable. Which one of these must it be?
That's in the first one.
It
Don't have
has-
the definition.
Because of this, right? So this will contradict this. Yeah, this is a contradiction, right, of that. So we cannot have that. So that means this thing is actually true. And it is not printable. Thanks to you, right? So we have shown that there is a sentence which is true but which nevertheless cannot be printed. Now, Smiley say, change the print, right? This printing to proofs. And then change your machine to a system. Right? So you now have a system that proves true statements, but there will be statements expressible in that system that are not provable. There are true statements which are not provable. Is that good? A bestseller, all those, right? It's amazing. And yeah, with that, right? So I just want to say a couple of things in terms of history. Why would Godel, so Austrian, right? We say he switched from theoretical physics to logic, to be more and more precise. Even so, why would he think of proving something like this? He must have.
To ruin Bertrand Russell's life work.
To show that Hilbert was wrong.
That's it. So you know a bit of the history.
A little bit.
However, Hilbert was the most respected, like for him. Even so, after he proved this, he said, no, I didn't contradict Hilbert when everyone said you have to. So you will read the history of it. But precisely, it's not Russell. Okay, Russell was also contemporary, and he had no, it's not like Russell, was competing for a girlfriend or something like that. No, he had nothing against Russell, right? And actually he was happily married. Also, I don't even think you read about Godel. And the wife didn't know any mathematics. That actually helped in some sense. Anyway, it was a reaction. It was not so much a reaction. He was trying to answer Hilbert's problem. So do we know who Hilbert is? Yeah. Right? Yeah, he is like one of the most influential mathematician, modern mathematician. And if you go far enough, like Z, for example, next semester you are going to take homological algebra. Well, I also wanted to, but like the time didn't quite work out for me.
It moved. It was Tuesday, Thursday.
I know it worked for me, and then after it moved, like homological algebra was also due to like kind of started by him and Congreve is another one, but they disagree philosophically, but they are both very. So anyway, Hilbert in 1900, he gave a lecture and he published 23 problems called Hilbert's problem. So 1900, most fittingly to welcome the century, the new century, what better thing can you do, right? To pose the most significant open problems. And some of them actually have to do with foundation of mathematics. So things like that. And so he has been interested in, consistency and completeness, right, of our axiomatic system for a long time, but only in 1920 something, right, and 30s that he went back to the work again. And due to two things, one was actually Russell, because Russell and Frege, they did such a good job with, the logic, like putting math in terms of logic, that Hilbert felt that he could, start doing things about this, consistency and completeness. But he was so optimistic about it. At that time also, he felt the urgency to prove this thing because he had another enemy. You know who? Very famous as well. Start with B. topology. Brower.
Oh.
Because Brower was somehow, after he did a lot of very significant math work, he got into this intuitionism thing that says that nothing is real. Like it's all subjective, it's all like mental construction and things like that, and which made Gilbert very uncomfortable. And so Gilbert said, I am going to refuse to silence him once and for all. By proving that, blah, blah, these things, okay, this desirable thing. And then Godel came along. Godel was very excited, obviously, and he happened at the right time. You know how old he was, Godel? That was Mozart. When he wrote his symphony on this, maybe he was 6. But anyway, yeah. When he yeah, so then he proved this thing. Okay, or rather disprove it. Yeah, so that's the history of it. And the rest, right? I think my purpose is to also maybe encourage or say that sometimes you can take a break from doing math and look at it, right? And read up some histories. Gilbert, I mean, he did a lot, but also after a long time, apparently he became interested in the big picture, okay, which led him to do these foundation things. Recently, actually, okay, for you guys, these young people in the room, when you do mathematics, there is another thing that probably will take off a question, right? It will be the role of computers, which is the other day, a PhD student told me, some of you know him, for me, he's a very nice guy, one of the best chess players. Yeah, so he told me that, oh, Professor Lee, I'm going to MSRI, which is a mathematical institute for summer school. Formalization of mathematics. I'm like, okay, what is it about? He said he doesn't know yet. So I look up the program. Have you used it?
But a few of us around here have.
You do your homework? So it is a computer proof assistant, right? Yeah, and so I look at this guy, CNU. He's a professor of philosophy and also mathematics. So I emailed him because I have a specific question. At that time, I also read about this. Nobody has heard of this one, I'm sure. This one. Lakato's. Yeah, it's fine. So he has a classic which you can read if you are interested in proofs and refutations. Okay, so he is kind of like an anarchist in the sense that people will try to build foundations here, right? But of course, there are different schools. Okay, so even Brower quarreled with Gilbert and also with Russell and all that. They all still want to build the foundation. And Lakatos say, forget about building foundation. It's all in vain. And let me say it. Yeah, let me see. He say, you know what math is? He proposed that, like math, like other sciences, is a body of fallible knowledge being improved incessantly in response to ongoing refutations, right? So you make some progress, you're refuted, then you make some more progress and all that. So it's a continuous process and variable, okay, at all times. So anyway, so that's his, but his is a bit too extreme in some sense, right? Yeah, and I asked this guy, I asked this professor is Jeremy Abdul, and he pointed me to a couple of very nice articles, right? About the nature and practice of mathematics. Actually happened. And he himself also wrote a paper on the role of computers in mathematics, in the practice of mathematics for future people. Because we do have this computer proof assistant Lee, some of you have used it, but that is about doing proofs, right? You have to formalize your system and then the computer can do it. But how about chatbot? Right? So I asked him, like the informal part, right? About this powering now we are talking about. Can chatbot engage you? And then so he sent me his paper, which he hasn't published yet. So he talked about possible interaction with other AI technologies, right? Yeah, where if chatbot develop to a point, they can engage you, they can engage mathematicians, right? Because they have seen enough examples, which they remember, unlike us, we forget. And then maybe by some machine learning as well. So all these things can come and have impact. And so it is possible, and anything is possible. So probably I will end with this note, right? I myself think the best thing, of course, is to be open, right? To be open about it and see what it is. Because you don't have to commit to a position until you have to, until you feel so strongly. So thanks a lot for, yeah. Does everyone want to share any thoughts? Or have any questions? Yeah.
I just noticed when you were putting this example up on the board, this is very, very similar to kind of Turing's solution to the halting problem, where you basically just take the statement, you kind of plug it into itself, and then you get that same exact. So very interesting.
Definitely, that's right. So when we were talking about it, Jonah and I were saying also that is actually an easier way to this. Yeah, and Turing, being the fourth mathematician on that picture, right? Where is my painting? Okay. Yeah, so that will be next year. What a year.
Looking forward to it.
Huh?
We're looking forward to it.
Yeah, thanks so much, everyone. Okay, so have a great summer.
Why did girl think?
If you showed up last week, get a QR code. Started at the night. Now.
Thank you. Welcome.
It's funny, Professor Garcia gave a talk on intuitionism earlier this semester.
Oh.
And last semester. The one last semester was a bit, was much more accessible, I think, than the follow-up, which involved, what was it? Constructing, or like you can construct all the possible models of intuitionism using like toposes over sheaves and stuff like that. So that was a bit more arcane, but it's very fun. This one too is also very interesting. So.
Thank you. Yeah.
I want to follow up on that because you had mentioned at the beginning, like sort of heard, perhaps other math talks as this year. And sort of something we've been talking about as well.
Right.
But ending the semester on this, I think, was a really nice way to conclude.
Something understandable.
Right, exactly. I think most people got at least something out of it. Yeah, I think it was a very successful talk, especially, it's also interesting that, now both these talks have almost been kind of like dialogue. The first one was more of like a plan, I guess this was just like, almost very kind of.
Yeah.
Yeah, I needed to bring in my